Hey everyone, this is Unit 8. We are starting our unit on stoichiometry. This is also really known as our quantitative chemistry unit because this is when we start actually measuring things in chemistry rather than just saying, oh, here it happened, here's the basic measurement. We're looking more at, okay, well, how much did we need to make it happen? Essentially, what we're doing now is recipes in chemistry. Okay? In order to do recipes, a lot of that involves grams. And so our first step is to kind of make the step from what we have been doing previously in terms of dimensional analysis to adding in another factor, including grams. All right, so before we get to the grams, the first thing to discuss is the concept of molecular weight. Molecular weight is the overall mass of a molecule. Pretty simple. If we know that a carbon atom has a mass of 12 AMUs, the atomic mass unit, and we know a hydrogen atom has a mass of 1 AMU, then a hydrogen plus a carbon would be 12 plus 1, which is 13. So calculating molecular weight is adding together the masses of each element in the compound, making sure you have the correct quantities. In the example I just used, I said carbon and hydrogen. Well, if there were 4 hydrogens, then I would add the mass of hydrogen 4 times plus the mass of carbon. So it is measured in AMUs because this is the mass unit we use for atoms specifically. It's the mass of a proton or a neutron. So by adding and subtracting neutrons, etc., that's the simplest way to adjust the mass of an atom. And so it is measured in the atomic mass unit, or the mass of one of those particles. So let's look at an example of calcium chloride, CaCl2. First and foremost, in our last unit, we learned how to count atoms. So in this, we have 1 calcium and 2 chlorines. So when we add up the molecular weight of calcium chloride, we need the mass of 1 calcium and the mass of 2 chlorines added together. So 1 calcium, according to our periodic table, has a mass of 40.08. 1 chlorine has a mass of 35.45. We multiply that by 2 because there's 2 of them. And then we add those 2 together to get a total molecular weight for calcium chloride to be 110.98 AMUs. So we're literally just adding the mass of the atoms, the mass of the elements. The mass that's on the periodic table is the average atomic mass. That's what we use. And so add those together in the correct quantities, and that's how you can get your molecular weight. So looking at a more complicated one, doing the calculations of this particular element in terms of counting the atoms, or excuse me, this particular compound in terms of counting the atoms, we have 3 magnesiums, we have 2 copies of phosphate. So that means I have 2 phosphorus and 8 oxygens. So if I had a PO4 and a PO4, that's 2 Ps and 8 Os, okay? So 3 magnesiums, 2 phosphoruses, and 8 oxygens. So I would take the mass of magnesium, 24.31, multiply it by 3. Take the mass of phosphorus times 2, take the mass of oxygen times 8, add it all together, and the molecular weight for this compound would be 262.87. So calculating molecular weight is literally counting the atoms, adding up the masses of each atom, and that's the weight of the entire molecule. So quickly go ahead and practice in your notes these 2. And then we can use that to kind of start next class to say, okay, let's do these 2. And we'll go over them, make sure that we got the right answers, and then we'll be on our right track. So practice in your notes calculating the molecular weight of H2O and SrCl2, so water and strontium chloride. Oh, and aluminum acetate. Sorry, I didn't realize it was the third one. My bad. So calculate those 3, please. Use your periodic table to get the mass of each atom, add them in the correct quantities, and we will check our answers tomorrow. All right, so we said something like calcium chloride. Well, calcium has a mass of 40. Chlorine has a mass of about 35. And in calcium chloride, there's 2 of them. So of that molecule, the vast majority of that element, or excuse me, the vast majority of the mass of that molecule is from the chlorine, being that there's 2 chlorines. So given that concept, one thing we do is calculating percent composition in a molecule. So sometimes we can actually take the entire mass of a molecule and say, okay, well, what part or what percentage of this entire mass is made up of that particular element, okay? And so the basic formula that's used when calculating percent composition of anything is part divided by whole times 100. And so even when you're doing, let's say, an exam score, the whole would be the total number of points possible on the exam. The part is how much you actually received, and then multiply by 100. Now, if the whole is out of 100, usually we can do it in our heads, but let's say that the exam was out of 75 and you got a 72. So it would be 72 divided by 75 times 100. That gives you your percent of the total possible points was made up of the points that you made. So this formula works for anything. The part in this formula for calculating percent composition is the mass of that particular element, or the mass made up by that element. The whole is the entire molecular weight. So again, using the example of calcium chloride, we have the entire molecular weight to be 110.98. So if we wanted to figure out the percent composition of each element in there, we would say, okay, well, if the total is 110.98, calcium makes up 40.08 of that. That's the part. So the part divided by the whole times 100 tells us that of the entire molecule of calcium chloride, CaCl2, about 36% of it is calcium. Doing the calculation for chlorine, about 64% of that molecule is made up of chlorine. Okay? So again, we're just taking the part that we're looking at, divided by the entire molecular weight times 100. Go ahead and practice these two in your notes again, and we will, like I said, use those to kind of warm up next class to run through and say, okay, what did you get? Here's what we should get. And if you made a mistake, we can figure out where it might have been. Okay? Now, the third thing here that we're learning about is really nothing insanely challenging. Now, follow along with me, okay? So we just learned how to calculate molecular weight. Molecular weight is in AMUs. But when I'm in the lab, I don't see that there's a device that measures AMUs in the lab. That doesn't happen. We measure in terms of grams. And so by measuring in terms of grams, we need to figure out, okay, well, if I need let's say I need an entire molecular weight of calcium chloride. I need that much calcium chloride. I need a full amount of that. I can't measure it in AMUs in the lab. But what I can do is measure it in grams. And in fact, the AMU to gram ratio is a 1-to-1 ratio. So if something has an atomic mass or a molecular weight of 10 AMUs, then if I were to measure it in grams, I'm going to measure 10 grams. So let's talk about what that ratio actually is. So we said the molecular weight is the mass of one molecule of that substance. I find the mass of the exact formula. That's one particle. That's one molecule of the substance. So the new term here is molar mass. Molar mass. So molar might make you think of moles, which, yes, 1 mole. Earlier in the year, we very briefly started learning what a mole is. We learned that a mole is basically a full set of an element or of a compound. So if I have a mole of something, I have what's considered a full, complete set. If I have a mole of calcium chloride, I have a full set of calcium chloride, which means I actually have 6.022 times 10 to the 23rd particles of calcium chloride. So all of these values that we've been working with are starting to come together now. We saw the 6.022 times 10 to the 23rd atoms or molecules in 1 mole. That's how many particles there are in a mole. And so the mass of that mole for each element may be slightly different, because if I have a mole of feathers, which would be 6.022 times 10 to the 23rd feathers, and I have a mole of bricks, 6.022 times 10 to the 23rd bricks, I have the same amount of each, but one is going to have a significantly higher mass because each individual part in that mole has a higher mass. So the mass of 1 mole of a substance is going to be a 1-to-1 ratio with the molecular weight of that substance. So the molar mass of a substance is a 1-to-1 with the molecular weight of the substance, but in a different unit. So molecular weight is in AMUs because we're talking about one molecule. Molar mass is in grams per mole, or grams most easily, but grams per 1 mole. And that is the mass of 1 mole of molecules of that substance. So this is just a vocabulary concept because it's not a mathematical concept. Don't get too deep into it. So 1 molecule, molecular weight, 1 mole of that molecule's molar mass. Quantitatively, numerically they're the same, the unit would be different. Okay, so it's a 1-to-1 ratio between AMUs and grams per mole. Obviously, grams is a much greater unit, so if I'm dealing with a mole of the substance, I have a lot more of it than I would if I just had 1 molecule of the substance. But it's that direct coordination or direct correlation between molecular weight and molar mass. So a mole is like a counting unit. You can have a mole of anything. It doesn't have to be just an atom or molecules or anything like that. So quite simply, if the molecular weight of calcium chloride is 110.98, the molar mass is 110.98. The only thing that's different is the unit. Molecular weight, AMUs, something we can't measure in the laboratory. Molar mass, grams, we can measure that in the laboratory. So we can measure the molar mass of calcium chloride. We can get 1 mole of calcium chloride. We can't measure out 1 molecule of calcium chloride. So it's basically like scaling up. Okay, so since we can't measure a specific 1 molecule in AMUs, we scale up to grams, which scales from 1 to 6.022 times 10 to the 23rd, or 1 mole. So we scale from 1 molecule up to 1 mole and scale from AMUs up to grams. So it's a direct scaling is essentially what we're doing. Okay, so yeah. The molecular weight and the molar mass are the same. They're calculated exactly the same. It's just a difference in unit. Molecular weight is going to be in AMUs. Molar mass is going to be in grams per mole. Okay. You don't need to practice this because, again, this is just a vocabulary thing. We'll dive deeper into it as we move into our practice next class. The last thing I wanted to point out, and this is something that we won't get too heavy into, but it's hydrated ionic compounds. So we calculated molecular weight. Pretty straightforward. CaCl2, 1 calcium, 2 chlorines, add it together, that's that, okay? But a lot of substances that are actually in our laboratory are referred to as hydrates. And what this means is that they are hydrated. They have water in them. They have water molecules stuck in the crystals. Well, water has mass. So if you're told that something is a hydrate, what we're saying is it has water molecules stuck in its structure, and they're going to add mass to the structure. So if I have calcium chloride, again, the molecular weight 110.98 AMUs, if I have calcium chloride as a hydrate, now notice there's just a dot and then it says 2 H2Os. So by writing that all together, we're saying this is a hydrate. This is something that in its crystal structure has water molecules stuck in there. And specifically, it says 2 H2O. So what we're saying is for every calcium chloride, there are 2 water molecules stuck in there. It's a ratio of 1 to 2 in this case. So water has mass. Calcium chloride, we say, okay, the weight of 1 molecule of calcium chloride is 110.98. But if it has 2 water molecules stuck in there, I need to add the mass of 2 water molecules to that. So the molecular weight of the hydrate in this case is 147.01 AMUs, because the mass of the 2 water molecules that are trapped inside are going to need to be added to the mass of the molecule itself. So the basic idea with hydrates, nothing crazy. It's just saying, oh, I recognize that this is saying, oh, lithium chloride and 4 waters, that's a hydrate. So when I calculate the molecular weight, I just need to add those waters into it. So we're saying the crystal structure is literally hydrated with extra water molecules. So we add the mass of those molecules in when we're calculating the molecular weight or the molar mass. If I needed 1 mole of barium hydroxide octahydrate with 8 waters, I would need to measure on the scale in grams, molar mass, grams. I would need to measure in grams the mass of barium hydroxide plus the mass of 8 waters, because those waters are locked in there, okay? So here, magnesium sulfate hexahydrate, I was being a little hateful, but if you want, it's MgSO4 and hexa means 6. So there's your hints, okay? Magnesium and sulfate, put those 2 together, and then hexa means 6. All right, so practice those 2. Again, you're just calculating essentially molecular weight here, but add in the mass of the water. If the water's stuck there, you add in the mass. It's basically like saying, okay, I have a basket of oranges, but there's an apple in there. I need the mass of the whole basket. Well, I'm not just going to measure the mass of the oranges. I would add in the mass of the apple as well. So that's the idea of a hydrate. I'm not going to just measure the ionic parts. If the water's stuck in there, it's adding mass, I need to add it in as well, okay? So to review, we hit on a couple things here. We're looking at molecular weight, we're looking at molar mass. Those are kind of the two big things we're learning here. Molecular weight is the mass of one molecule. The molar mass is the mass of 1 mole of that molecule. It's a perfect 1-to-1 scale up ratio from 1 molecule in AMUs to 1 mole in grams per mole. The only thing that we then added in to say after that is, well, in addition to measuring the entire molecular weight or molar mass, sometimes we need to measure what percentage of that mass is certain elements so that we can try to figure out some other things about the compound. Or sometimes we need to also factor in the idea that there may be water molecules stuck in the crystal structure like there are with hydrates. These are extremely common. Pretty much everything that we work with in our lab is likely sold as a hydrate. It stabilizes the crystal a little bit, so that's how it's sold, and so that's how we work with it, okay? So molecular weight in AMUs, 1 molecule, molar mass in grams per mole, and that is 1 mole of molecules, 1-to-1, percent composition, and how to deal with hydrates. Those are the 4 big things from this. So we are going to be practicing next class. Do these practice that it says to do in your notes. We'll use that as our warm-up to go through those, start practicing, and move forward. I will see you guys then.